to differentiate it from the last one. So everyone, welcome. We're going to start in just 1 or 2 more minutes. Thank you so much for joining us.
Okay, can you hear me now?
Yes, we can hear you now.
Yeah, there's some kind of major internet problem going on at my house, so I'm rebooting my router, but I'm on my phone, so
okay,
should be good.
Okay, thank you. Thank you. We can hear you nice and clearly. That's awesome.
Great.
So welcome everyone. I anticipate that we'll have more people continuing to join us as we get started. We are live on YouTube as well for anyone who's having trouble joining us by Zoom. And you are welcome to post comments on the YouTube channel, and Yolanda will share those with us. Sherelle, would you mind going ahead? Do you have the PowerPoint? Can you share the first slide? And Sherelle, please go ahead and tell folks a little bit about who we are.
Well, hello and welcome everyone. Welcome to the live from LPSC 52 to our virtual experience. So welcome to everyone, and we're so happy that you decided to join us after this long day, but we're going to make sure that you enjoyed it. So please make sure that you're entering your questions in the chat box for all of our panelists. Enjoy the discussion. We are here to listen to what you experienced today. And so our panelists are ready to answer your questions, whatever they may be. So let's get started. Well, my name is Sherelle Webb. I'm an education specialist for the Lunar and Planetary Institute, and I am excited to be here. I actually, before all of that gets started, I wanted to introduce you to the rest of the people that are here as panelists. I'm going to start with Yolanda Ballard.
Well, hello, everyone. I am Yolanda Ballard. I am one of the program coordinators for the education department, and I am going to be working in the background today, making sure that the live stream on YouTube is going well without any glitches. And also feel free to send any messages via the chat if you have any questions or lose your connection. I'm so excited to have you here and glad to be able to be here with you. Thanks.
All right, thank you, Yolanda. And next up is my phenomenal manager, Christine Shupler. Go ahead.
Hi, everyone. We're glad to have you with us. I hope that some of you are joining us again from last night and will continue to join us this week. Thank you for coming.
All right. All the way from Hong Kong. Hail, Dr. Inglis. Go ahead.
Hi, I'm Angelica from University of Hong Kong. So I've been the whole night listening to the talks, and it's 8 in the morning in Hong Kong. So I'm ready to talk a little bit about what happened today in the conference.
All right, Ms. Kumari, go ahead.
Hi, I'm Nandita Kumari from Stony Brook University, New York, and it's evening here, and I'm a second-year grad student, and I am pretty much excited to discuss the new results that we came to know about today and yesterday, and from the posters.
Awesome. Michael?
Hello, everyone. My name is Michael Zallenhofer, and I am a recent graduate from Northern Arizona University, and I'm excited to just chat with you about today's program and also about some of the posters that are upcoming as well.
Awesome. Miss Lori Pig.
Hi, I'm Lori Pig. I'm a PhD student at Northern Arizona University and a Pathways intern at the USGS Astrogeology Science Center. And I was a microblogger. I presented today, so I'll just sort of be in the background adding some input from that session.
And last but certainly not least, Dr. Ken Williford. Take us away.
Hi, everybody. I'm Ken Williford at JPL, and I'm a Deputy Project Scientist for Mars 2020, and really happy to be here and talk to you today.
Thank you so much, Dr. Williford. So before we go any further, I want to say a few things for all of our participants and attendees. You may notice that we have closed captioning ongoing on this. You can turn it off. If you have joined us by Zoom, where it says live transcript, just click on the up arrow and hide subtitle. And that way, if it's distracting you and you don't want those subtitles there, click on where it says live transcript, click the little up arrow and hide the subtitles. Or if it isn't turned on and you want to turn it on, click on show the subtitles. So, and then we also have a question for all of you who are joining us tonight, question about you. So folks, what is your own background and interest in planetary science? Please let us know. Are you curious about planetary science? Don't know much, but you want to know more? You enjoy learning about the solar system? Are you studying planetary science? Are you a solar system ambassador? Are you an amateur astronomer? Are you a planetary scientist? Are you attending a conference right now? And I'm going to give everyone 5 more seconds to select their choices. And if you are joining by Facebook, by YouTube, you are welcome, of course, to also enter your thoughts in this chat if you would like. So 4, 3, 2, 1. And we've got a big variety here. Some of you would like to know more. A lot of you, of course, enjoy learning about the solar system. Some of you are studying planetary science. Quite a few of you are. And quite a few of you are actually attending the conference. So thank you so much for that. Sherelle, Miss Sherelle, would you mind moving to the next slide, please? And here's just a little bit about the Lunar and Planetary Science Conference for anyone who is joining us tonight isn't aware of it. It's held annually in March. It's sponsored by the Lunar and Planetary Institute and by NASA Johnson Space Center. And it brings together international specialists in a variety of topics to present their latest research in planetary science. And we'll post these links for you in the chat in a bit, so to make it easier for those of you who want to go check it out. Or all you have to do is just Google LPSC 2021, and that should take you there as well. Sherelle, can we go ahead and move to the next slide? And here's a little bit about what we're planning for tonight. So we've already started our introductions, and we're going to have a short interview with Dr. Ken Williford. And then we're going to have a panel discussion and a question and answer. All of you who are attending, start thinking now about what questions you have for all of our speakers. And please, if you have comments, we'd love for you to share your comments in the chat box. Go ahead and post them. Oh, we're not on YouTube. Let me go ahead and make sure that we get that streamed now. We should be.
I think we're good now. I see a thumbs up from Yolanda.
Okay, we're good. All righty. But please, if you want to add things in the chat box, please select panelists and attendees so that other people can see your comments as well, because this is meant to be a discussion, and we'd love to hear from you too. If you want to speak using your microphone at any point, please put your hand up and we'll go ahead and give you microphone rights as well. Next slide. And all of our speakers tonight have already introduced themselves, but here's just a sort of a reminder as to who we've got with us right now. Dr. Ken Williford is going to be speaking first, and then our panelists are going to be joining in and sharing some of their thoughts about today, about the most exciting aspects of today, about which talk they heard that they were most excited by, or that inspired them the most, or that they thought was meaningful, and why it was particularly important. So let's proceed. And here we are. And Sherelle and I are going to be taking turns asking everyone questions. And so I'll go ahead and I'll kick off here with our first question for Dr. Williford. Of course, with your position with Mars 2020 and the landing and everything, first of all, what aspect of its arrival on Mars has excited you the most?
It's just been such an incredibly exciting time. The time has sort of flown by. It's a crazy time in that we're all working on Mars time. So imagine a lot of the people participating know a little bit about what that means, but for those of you who don't, the Martian day length is a little bit different from the Earth day in terms of time. And in order to get the most efficiency out of the rover, we work on Mars time. So the scientists and engineers do our work to look at the newest data that have come down, decide what to do next, and actually eventually write the sequences and validate the sequences that will get beamed up to the rover so that it can do its thing. We do all that during the Martian night while the rover is asleep and charging its batteries. And then we go to sleep right before sunrise on Mars. Right after having beamed up those commands, the rover wakes up and it does its thing while we're asleep, and we repeat. And our work day that corresponds with the Martian night, because the Martian and Earth day length are a little bit different, the Martian night sweeps across the Earth day. And so sometimes we're working in the middle of the night, sometimes we're working normal hours during the day. So it's kind of this added to all the excitement is this craziness in terms of our sleep schedules. And but it ends up in a sense being, at least at the beginning here, there's a lot of adrenaline going on, and we're getting, every new picture is something totally new to us. And so our curiosity is in overdrive, and we're so excited to see all the new data. And so it's sort of an added little element of fun, just staying up all night, working together with the engineers. And so it's just, it's hard to point to one thing, but we're just, every new picture that comes down is so exciting. I guess one thing that had us all completely floored were these entry, descent, and landing camera videos, the EDL camera videos. It was this system of cameras placed all around different parts of the spacecraft, and it captured for the first time the entry, descent, and landing sequence. And those videos, we watched them like all of you, I imagine, just absolutely astounded by what we saw. So it's just all very exciting, and the potential is enormous.
Thank you. Thank you. Let's go ahead and let's move on to the next picture. And we have our first question for you already. So here, can you tell us just a couple words here about sort of this photo of where it landed and about the delta there? Ken, you're on mute.
Yeah, I'm sorry, I'm not seeing the picture, so I'm
okay.
sorry about this, having
no,
all these yeah. Okay.
No worries here. So I'm showing the picture of the Butler landing site, and it's showing the delta, and it's all grayscale, so it's not with the artificial colors. And in the upper left, it looks like the delta flowing down. And over on the right, we've got these little dark areas throughout. Are those all craters? What are those?
Yeah, there are plenty of craters around us. So we are sitting right in between two geologic units that we've mapped. So the science team put together a geologic map of the landing site. And to our east is this sort of heavily cratered area we call the crater floor fractured unit. And we're really interested in that. In some of the earliest studies of Jezero, this unit was mapped as the crater floor volcanic unit, thinking that it was a volcanic rock. We know that its mineralogy is consistent with it being a volcanic rock. On the other hand, especially after MSL, one of the things that we've learned from Mars is that almost all the rocks that we see have a mineralogy that's consistent with a volcanic rock, even when they're sedimentary rocks. So a lot of the sedimentary rocks that we've been exploring with the Curiosity rover were originally volcanic rocks that were eroded and then redeposited as a sedimentary rock. So we don't know if these rocks right around us are igneous or sedimentary. And both are very exciting, but that's our first big scientific mystery to solve. and we're right in the middle of it right now. And so I talked about that crater floor fractured unit. Crater floor fractured rough unit is the unit to the east, and it's rough because it's very heavily cratered. And then just to our west, there's this feature that we call Sita, and it's this sort of erosional feature, strange geomorphic feature. It kind of looks like a mitten. Sometimes we call it the mitten, but we're using this word Sita, which is a Navajo word that means, I believe, among the sands. And that's because there's a whole lot of sand dunes in the middle of this feature. And the rocks that are underneath the sand dunes are what we call the crater floor fractured unit, as distinct from the crater floor fractured rough unit. And those two units have very distinct mineralogy as observed from the infrared spectrometers in orbit around Mars, the CRISM spectrometer primarily. And it looks like the crater floor fractured unit, which is inside Sita, is olivine bearing. And some of the olivine bearing rocks, that's a mineral, some of the olivine bearing rocks around the region where we are also seem to have carbonate minerals associated with them. And so that's extremely exciting. So we'll be looking forward to see if we can find any carbonate minerals in there. Whereas the crater floor fractured rough unit, more off to our east, is dominated by pyroxene and does not have that olivine signature. And so we're just trying to figure out what all that stuff is. And we'll spend the next several months cruising around there, exploring those rocks, and then eventually make our way to the delta and ascend the delta and move on from there.
And just to clarify for anyone, when carbonate minerals are particularly exciting because they form in water, are there other reasons that yeah?
There are many reasons. So one of the most exciting reasons is that carbonate minerals on Earth are often associated with biology. Mm-hmm. And so carbonate, one way carbonate minerals form on Earth is in shallow water environments. They often form at low temperatures. At low temperatures, we mean temperatures that we find at the surface of the Earth, as distinct from high temperature geologic processes that you find deep inside the Earth, like an igneous rock. We often find carbonates forming at low temperatures on the surface in shallow water environments. And especially, so think about coral reefs. They're all made of calcium carbonate, and seashells are made of carbonate minerals. And so not only do carbonate minerals form in environments that are often inhabited on Earth, they also help to preserve signs of any life that's in those environments. And so they're great potential targets for astrobiology. Now, of course, we do not know if these carbonate minerals in Jezero have anything to do with life whatsoever. They're just kind of a tantalizing hint of a mineral that on Earth is often associated with life. But no matter what, even setting aside all the astrobiology, whether or not life ever existed on Mars, the carbonate minerals that we see around our landing site almost certainly represent processes that happen at this interface we call the critical zone, where the atmosphere, the hydrosphere or the water on the surface of the planet, and the rocky part of the planet, where all of those things come together, that's where you find carbonate minerals forming. And so they lock inside themselves. They're like little time capsules that record a record of those interactions of the ancient Martian atmosphere with water and with solid rock. And so we're excited about the carbonates, irrespective of the astrobiology, but they really kind of get our attention in terms of habitability and biosignatures as well.
Thank you. Sherelle, can you go ahead and move to the next slide? And while you're doing that, Josh had asked how long is a Martian day, but Ken pointed out, a different Ken Brand pointed out that it's 24 hours and 37 minutes. And this next slide has a map showing the track of the pathway that's intended. And it's got a yellow pathway going up into the delta, but it's also got sort of a little circular pathway that's blue and purplish going around in a circle. And that connects to a question that Bill asked the delta looks elevated. Can Perseverance climb that?
Yes, we can. And by the way, now I can see the shared screen. Sorry.
Okay.
And yeah, it is elevated. It's about 40 meters high off the crater floor there. And that yellow path you see is a path that we've looked at both from a scientific point of view, where we'd like to go scientifically, but also where our rover planners believe it's likely that we could traverse.
Awesome, awesome. And someone else had earlier asked about the rocks that have been blasted by the Chem-Men already, whether you think they are sedimentary or igneous. Is there enough information yet to tell?
There's not enough information yet to tell for sure. So that question is still open. I would say, so clearly they have a, mineralogy, as I said, that's consistent, and an elemental composition that's consistent with them being a basaltic igneous rock. For the less geologically inclined, that's the kind of rock that, Hawaii is made of, and most of Mars is made of. But there are some tantalizing hints that they could be sedimentary as well. So we'll just have to wait and see.
All right. Folks, please continue to post questions for Ken and also questions that you have for the rest of our panelists. We'll be getting to them in just a couple more minutes. Ms. Sherelle, would you mind switching to the next slide, please? And here we've got some of the pictures that have been taken so far. For these rocks, can you comment a little bit on the bright and dark and the difference between the bright and dark ones that we're seeing right now?
Sure. So it looked like, and maybe an animated GIF of some of the NavCam images taken during a drive. So that's a pretty cool animation that you have. And so we do see, I said in an early press conference, we have, our first observations we've been making are we have light rocks, dark rocks, and holy rocks. And so you can see some of all of those here. And a lot of the, so the rocks that sort of have a rough texture in the middle of the scene there are what we call the holy rocks. You can see some of those holes in them. That's HOLEY. And the first thought that some of our team members said when they saw these was, oh, it looks like vesicular basalt. And so vesicular basalt's a kind of basalt that has vesicles, and vesicles are holes that form when gases escape from the rock as it's cooling. And then those, so think of those bubbles, gas bubbles cooling and crystallizing as holes. So they do look like vesicular basalt, but we definitely do not know that they're vesicular basalt. So instead of calling them vesicular, we started calling them holy to try to stay away from any interpretation and lock ourselves into one model or another, because we also see that at most to maybe all of the Mars landing sites, we see examples of this, and they are not necessarily basalt. So you can get holes like this forming from pitting that occurs from aeolian, that is wind abrasion. So most of the erosion that's happening on Mars today is just basically sand blasting. So you see all that sand in the scene, the wind comes along and whips that up, and the sand hits rocks and can create little pits that are then accentuated over time and can form holes. So those could well have nothing to do with vesicles. Then you asked about the light and dark tone. Those differences in tone are probably caused by variable dust cover. So Mars is an extremely dusty place. There's dust everywhere on Mars. And there was a funny exchange on our sort of science team chat tool where, some of our science team members who haven't been on missions before were making some interpretations about the colors. And this old experienced Mars rover guy was saying the first rule of Mars images and color is it's dust is what's causing the difference. The second rule is that I can't do it as well as he can, but it's something like, see rule number one, it's like it's dust is the reason for all things on Mars. And it's not as simple as that, but we see some of these rocks that appear to have their dust cover blown away. And when we've shot them with the SuperCam laser, one of the things that does, besides give us great geochemical data, is blow the dust off. And you see that under that light tone, it's a dark gray. And so probably most of these, even those light tone rocks, are actually dark gray underneath that coating of dust.
Awesome. Thank you. And I think I have one more picture, one or two more pictures. Let's go ahead and take a look at the next one here. And so this one's in color, yay, and it shows the tracks. I'm going to open it up right now for, there's a question actually from the, that has been posted probably from the YouTube channel by Yolanda. So are these rocks that make clouds, or are those only meteor smoke? That's, that might be in reference to, I'm not sure whether that's in reference to an earlier slide. Are these the rocks that make clouds, or are those only meteor smoke? Does anyone have an interpretation for that question? I think auto type probably.
I don't know. Maybe we could ask for
Christine,
some clarification from the, yeah.
Remember,
Yolanda?
we are a few, we're
Seconds
behind on the YouTube. And so it probably is in reference to an earlier slide.
Let's go back 2 slides and let's see if we can figure out a little bit here. Let's go, that's forward, backwards. One more, let's go. No, let's, so now let's go to the slide that we were on, the gray one with the rocks. So, and let's just stay here. If anyone has an idea about how to interpret that question, I know that autocorrect sometimes takes words and changes them, so it makes it hard to understand. But for this slide, I was going to see if any of our attendees or our panelists or Dr. Williford himself have a question that you'd like to ask or something that you'd like to comment on here.
I will say you can see the drill, the core in this image, and it's that sort of honeycomb cylindrical thing on the left side of the image, and then the white box that's pointing at us, that's the pixel instrument, the microfocus X-ray fluorescence spectrometer that maps elemental composition, and then that black sphere to the left of pixel is the gas tank, the nitrogen gas tank for our gas dust removal tool. So out on the other, you can also see Sherlock, which is right on the opposite side of the turret from pixel. So you can kind of see the back side of the Sherlock instrument, the laser, UV laser Raman and fluorescent spectrometer. Awesome. And then of course the robotic arm is there in the image.
Cool, cool.
You can also see the bit carousel where all the drill bits are. It's sort of dish shaped, like almost UFO shaped. There's that funny symbol sitting on top of it. That's where all the drill bits are. And so the robotic arm, the drill docks with that bit carousel, exchanges a drill bit, and it moves it around inside the body of the rover. There's a little robotic arm that puts a sample tube in, and then it rotates back around. You drill a core, put it back in, rotates around, and then processes that core inside, seals it up, and eventually drops it on the surface.
Awesome.
Dr. Williford, how powerful are the winds on Mars?
The winds?
Yes.
They are, I would say sort of 10 meters per second is 10 to 15 is not uncommon of a wind speed. But the atmospheric pressure is lower. So, maybe it wouldn't feel as powerful as the same wind speed on Earth, but it does blow sand around.
Okay, well, awesome. The symbol that's like not in the exact center of the screen, but the symbol that we're seeing in black and white, what does that symbol means or represent?
Yes, I wish I had a better answer for you, but what I think those are for, they are something like fiducial marks. So they're made to be easily recognizable for computer vision. So I think it's a way for the rover to know, sort of where its parts are in space. if that helps. You'll find them all over the rover in different spots. But it's basically something that the computer can easily recognize in an image taken by the rover and know which part is which.
Oh yeah, now that I see your, like here,
Yep.
I see it, and then here as well.
Mm-hmm. They're like little QR codes.
Yeah, awesome. Thank you.
Mm-hmm.
Thank you. And there's some speculation that the question about rocks and clouds might be about noctilescent clouds appearing at 80 kilometers above the Earth. Do any of our panelists want to comment about atmospheric clouds and their relationship with rocks or processes?
There are clouds, and in some loose, indirect sense, they have relation to the solid planet. But yeah, I wouldn't say, if I interpret that question, they don't come from meteorite impacts. And yeah, I mean, if there's an impact, maybe it can help generate a cloud. But the clouds just come and go on Mars, basically unrelated to the rocks and the meteorite impacts.
Thank you. Thank you. Well, Sherelle, would you mind, let's stop sharing the slides for right now, and let's do a sort of a whole group discussion on a variety of questions. And for all of our speakers, there's a request if we could also, when you're making measurements and sizes and scales, if you could refer also to English measurements in addition to kilometer. For some of us, some people have trouble, with both combined. My first question for our panelists is, I invite you to kind of share something today that you saw or heard that you thought was amazing or awesome or exciting. And who would like to go first?
Can I just, while people are thinking on that last point, the conversion of measurements, so just hopefully it helps some of the audience. So when we say a meter is just about the same as a yard. So think about a yardstick, and a centimeter. Think they're about 2.5 centimeters in an inch. Okay, so hopefully that helps. A centimeter is maybe about the size of your thumb or one of your fingernails. Hopefully that helps people.
All right, Christine, and I want to go, before we go too deep down, I want to go ahead and ask Josh's question. When the rover takes soil samples, how far does the drill go down? How far does it drill down?
About 6 centimeters, so a couple inches. a little more than 2 inches, 2 to 3 inches.
Thank you. Thank you. So, Nandita, was there something today that you saw or heard that you would like to share that you thought was particularly inspiring or interesting?
I think the Mars live sessions and the first results from Perseverance were really exciting. And I was just very excited to hear the talk by Dr. Jim Bell about Mastcam Z and his interpretations. And overall, the instrument as well, it was pretty awesome and wholesome, I would say. I also spent a lot of time visiting posters today because I just feel that posters have, since they do not have a defined time slots, there are very few visitors because we want to visit the talk and the posters, and it's kind of tearing us apart that way. And I saw quite a lot of posters using machine learning algorithms for detecting earthquakes and automating the detection of earthquakes quakes on Enceladus, and then detection of fresh craters on Mars, and like a lot of other things. And it was pretty cool to see this, machine learning gaining popularity in the community altogether. And I really look forward to these papers if they convert them to papers sometime in the future. Others can go ahead.
Thank you. So who would like to go next?
I can go next.
Thank you, Angelica.
Well, it was really hard to just choose one or two things because there were so many things going on. But I think one of the most important things that I found today is the carbonate rocks talk about, the carbonate rocks, not only outside the Jezero crater, but also in the crater rim. So Dr. Williford was already talking about that. So I will not repeat it, but I just wanted to say that since it's going to take some time to get there and to get some analysis, the speaker was talking about doing some comparisons at the moment with satellite images with the CRISM instrument and some topographic relationships. And at the moment, the result, it seems that these carbonates from both the crater rim and outside Jezero crater, they both look very similar. So it's something really to look forward and see what is the origin of these carbonates. And also, I was just taking a few of the posters, and I saw a couple of them related to human exploration of Mars. Really interesting. One of them was about resource utilization. So, of course, something to really think about if we're going to go in the future to Mars, to use the resources there to help with the payload here. And then the second one is about a subsurface habitat. So there is a design of a habitat that will go down at night and it will come up during the day to use the solar resources, and at night or during a solar storm or to protect the crew from the hostile environment, it will go down with some sort of hydraulic system. So I thought it was something to really think about, not for the near future, but really interesting poster.
Thank you. Thank you. And Dr. Zelnhofer?
So I focus mainly on the Mars sessions, and I have an interest in Mars, just I think like anybody else. And I just found most of the talks really exciting. I used to do some impact rating work on Mars in Arabia Terra, and looking at fluvial and glacial morphologies, and just seeing all the work that's being done with the Mars 2020 and what the next steps are. It just was really exciting for me.
Awesome. Actually, we've got a question about Mars here from Josh. How long does it take to send instructions to the rover from Earth to Mars?
It's about 10 minutes or so.
It looks like we've got another question. Sherelle, I'll let you read that one in a second. But before we do, let's go ahead and let's do a poll and get all of our participants to join in here. Our panelists, our scientists, people who attend LPSC, have a variety of planetary processes, topics that they study, not just individual planets and moons and asteroids and comets and dwarf planets and everything else. But in addition to that, people sometimes focus on individual processes. So I've got a list here of 10 different processes or topics. And this is one where I'm not letting you pick multiple choice. You have to pick one. I'm going to give everybody it's going to take you a couple seconds to read them all. So I'm going to give you 10 seconds to finish selecting one and voting. And while you're voting, Ms. Sherelle, would you care to ask the next question?
Absolutely. All right. So since Mars 2020 is a sample return mission, what measures are we taking to make sure that the Martian soil sample is not introducing contamination potentially harmful to Earth, but at the same time preserve any possible signs for life in the sample?
I guess I should take that. Yeah, that's a fantastic question. We've put a ton of effort into that question. What you're talking about is planetary protection. And I could go on, but I'm going to keep it really short. And so first of all, Mars 2020 is the first leg of a sample return campaign. And so it's our job to select the best places to sample using all of our scientific instruments, to collect those samples, to seal them up on board the rover in super, super clean, I'll call them hyper clean tubes. So we put a huge amount of effort into making a drill and a sampling system that could collect those rocks, seal them up in a way that they're very, very clean, and they have the minimum amount of earth stuff in them. And then we deposit them on the surface of Mars. Then they sit there, and 2 more missions, which are being developed currently jointly between NASA and ESA. One is an orbiter and one is a lander. And the lander has a little rover on board and a rocket on board. So the lander lands near our samples that we've put on the ground. The little rover goes out, gets our samples, brings them back to the rocket, launches them back into orbit, and then the orbiter rendezvous and captures those samples, flies them back to Earth. So they have to be, another major part of that deals with planetary protection is that our samples go inside this spherical thing called the orbiting sample. That thing, so the orbiter has to rendezvous with that and capture it in a way that the thing that captures it doesn't touch the outside of that orbiting sample. So the idea is that the outside of the thing that comes back to Earth, nothing on that can have touched anything that has touched Mars or has interacted with Mars. And so it has to kind of imagine it floating in there, closing shut, and then welding it shut in space. That's one of the options they're looking at. But it's basically triple sealed, and then it comes back to Earth and lands on Earth. And so extra special care is taken to make sure that even the absolute worst case, it smashes down into the surface of Mars, into the surface of Earth, which is probably what it will do for reasons I won't go into, not even have a parachute. It'll just come in, land in the desert, and we have to be very, very sure it won't crack open, and that people can go and take it into a super secure facility to open it up in a way that's safe for humans and completely contained. And that'll be the first round of work that's done, is to demonstrate that Earth safety before really the scientists get to do a lot of work on the samples.
Thank you, Ken. So before we continue with a few more questions that we've got about Mars, did any of you hear something that wasn't Mars related that you would like to share today? And Lori, I didn't include you last time, so do you have anything that you'd like to say, or do any of you have something beyond Mars that you wanted to say before we continue with Mars a little bit more?
I did attend the 2 sessions on volcanism throughout the solar system, the one Great Balls of Fire explosive volcanism, and Let It Flow, which is effusive volcanism, explosive volcanism being those explosive eruptions that shoot great balls of fire into the air, as the namesake, and then effusive volcanism, those lava flows. And it was really cool to see how each camp treats their different types of science, how they model their science, how they do all of the different things that they do, because these 2 sessions were about all of the different planetary bodies throughout the solar system. So Great Balls of Fire was about Mercury and Venus and the moon, and Let It Flow had sessions about Enceladus and Europa and all sorts of different planetary bodies. And it was really cool to see all of the different types of science going on. One thing I really liked in the Let It Flow session was one of the scientists was modeling how these lava flows come out of areas like Hawaii. And they made an analogy as a whole bunch of sugar grains, sugar granules packed into a container, and then you have flow moving through that sugar grains, and how is this going to change throughout the lava flow. So I thought thinking of lava in those sorts of ways was a really cool way to think about it.
Anything with sugar, that's awesome. That's wonderful.
I attended this session about volatiles, and particularly lunar volatiles, and they were so when we usually talk about lunar volatiles, we start with permanently shadowed regions in the South Pole, but today's session went beyond that, and about detection of H2O in central peaks of the craters, which are not on the in the polar regions. And one I would say one like question that the lunar community has been trying to answer for a while is, was moon wet in the past? And they have found water in the central peaks of the craters, which are not in the polar regions. So now they're like doing further detailed analysis whether it was, brought in by the solar wind or it's intrinsic to the crust. If it's intrinsic to the crust, that means moon also had water in the past. So that was a pretty exciting thing that I'm really looking forward to. And other than that, we also see a lot of again, water in the crystal in rough pyroclastic deposits on moon. And someone was using that to explain that, there is a very good possibility that moon was wet because leaving apart the central peaks, which actually we can't really leave apart. Pyroclastic deposits are more or less volcanic product. So they have to come from the interior. And if they have water, it means the interior of moon had water. Those were pretty exciting talks, I would say, other than like Mars altogether. Yeah.
Nandita, Josh posted a question about where the water came from, and then he said, yes, you just didn't answer that live right now, that it might have come from the inside of the moon, but you also mentioned potentially the solar wind. Could you clarify for everyone that we're not talking about rivers and lakes on the moon? How much water are we talking about here?
So I cannot really quantify that. I'm sorry about that. But when I'm talking about water, or when we talk about water on moon or any airless body per se, we usually talk about water in either crystal structures. There are certain minerals which can hold H2O in their structures. And that's what we mean, what we say that there was water on moon. I'm really sorry that I cannot come up with a quantifiable number, but that's again other than like the permanently shadowed regions which lie in the polar part of the moon. In poles, the story is a little different, since the regions have remained in darkness and like without sunlight for a really long time. We might see actual ice crystals. We hope to see, I would say, we do not know yet, but we hope to see actual ice crystals there. But we'll see. Now we have like missions designed to like a lunar South Pole. Just adding on a little bit about South Pole, the pits that Angelica was talking about in one of the Martian posters. I also saw, I think, a poster again on moon. So usually the pits that have been identified on the moons are again not in the polar region, but rather in the equatorial region more. So this poster particularly identified pits in the polar region because again, most of the plans for Artemis are for the South Pole. A lot of, I would say, not most, but like the first few phases are like towards South Pole most, and pits can prove to be useful for like different resource and I don't know, maybe this is a long stretch, probably habitability. My advisor wouldn't really agree to that, but well, that's that. So yeah, that was pretty cool.
A question for anyone that would like to go at it first. This has come from a YouTube, so thank you to our YouTube viewers. Thank you for sending us your questions. The question is, why couldn't the samples be collected by a manned rendezvous mission in Earth orbit and then brought home? Any takers?
Yeah, I'll take it. Yeah,
awesome.
They could be. So, and in fact, it's a great question, because that is one of the models that's been considered. I think we would call it the nominal approach, the baseline approach currently would be just to have them come straight back. But it has been considered to put them in Earth orbit and brought home by astronauts. So we'll see what happens.
Okay, thank you. I'm gonna follow that up with, I have read that liquid water can exist around solid grains trapped between minerals and ice. Would that be sufficient for bacteria, and could Perseverance check if liquid water was present in films?
Yeah, anybody else want to take this? I definitely can, but we have any other astrobiology oriented folks?
I think you should take it.
Okay. Yes. So let me just make sure I understood the question. Liquid water can exist around solid grains trapped between minerals and ice. Yeah, I mean, let's see. Could Perseverance check if liquid water was present in films? I think it would be tough for us to understand whether liquid water was present in a film 3.5 billion years ago. To get that level of detail on exactly how the water was distributed in a substance. But this might get to a very important distinction that everybody needs to understand. And so when we talk about looking for evidence of life, seeking evidence of life on Mars, we're talking about seeking evidence of ancient life, and it's extremely ancient life. So between 3 and 4 billion years ago, when Mars was a much different place than it is today, much more habitable, abundant surface water, much thicker atmosphere. And so we are not looking for evidence of what we would call extant life, that is, organisms that are alive or recently deceased. Now, one could send a mission to do such a thing, and there are various concepts for doing that. And it is possible that Mars is currently inhabited, but I would say most folks who study this would agree that if so, any organisms or habitable environments are confined to the subsurface and maybe even the deep subsurface where liquid water is stable on Mars. The low atmospheric pressure means at the surface, water just sublimates. And so any liquid water would just instantly evaporate. So it's hard to get a habitable environment. Now, you might be pointing to some things like RSLs, the recurring slope lineae, and there's been suggestion that these result from brines, and some of the processes like you're talking about, films of liquid water trapped between ice and minerals, and could well be that there are processes like that on the surface of Mars today. And you can imagine how little tiny habitable microenvironments could be generated there, but that's not what Mars 2020 is about. And in fact, because of the question that came earlier and planetary protection and so forth, we actually had to only consider landing sites where there is little to no chance of liquid water being anywhere close to the surface, or ice for that matter, anywhere near the surface at our landing site. And so we don't expect anything like that where we are, but we have plenty of rocks that used to be in the middle of a giant lake. So we're happy about that.
Dr. Williford, I'm so happy that you revisited that question, because I have a follow-up. How have we ensured we haven't brought Earth microbials along with us to Mars?
Right. Well, this is part of planetary protection. So most of what I talked about in the last answer on this was planetary, protecting Earth from contamination by Mars organisms. We also have a lot of requirements, very strict requirements, to protect Mars from undue contamination by Earth organisms. Now, from that point of view, we would all love to have been able to send a perfectly sterilized spacecraft to Mars. But it turns out that you can't get the level of performance and complexity that we want to do the kind of mission we want. That is to have the radioisotope thermal generator, our sort of nuclear power source, and a number of other aspects of our rover. It's not possible to build those things and have them be completely 100% sterile. So what we do instead is everything gets cleaned at what we call the piece part level, and then they get assembled and then re-cleaned again. Certain elements of the spacecraft, I mentioned the sample tubes, those are totally sterile. So we have a requirement that there can be not a single viable Earth organism inside that tube. And in fact, the whole chain of stuff that needs to collect a sample and seal it up, in that whole process, we have to demonstrate an extremely low probability of even introducing a single viable Earth organism into that sample that gets back, because we don't want to confuse ourselves on the way back. But we don't have to demonstrate an absolute zero probability of introducing an Earth organism into the Mars system, because we couldn't get the level of sophisticated rover that we want. we have a we have to keep what's called the bioburden, the number of organisms, very, very low. And the way we achieve that is by building things in very clean environments, cleaning them again, swabbing every surface, and culturing those swabs to determine how many organisms actually are there. And there's a whole group of planetary protection engineers who are in charge of ensuring that. And the MSL and the Curiosity rover easily met their planetary protection requirements, or met them with room to spare. We use the same approach, and I can confirm as well that we're well within our requirements for how many organisms we introduce to Mars. And then the last thing I'll say is that remember that the surface of Mars is so deeply inhospitable to Earth organisms. So anything that did survive that harrowing trip to Mars would almost certainly die pretty quickly in the Martian environment with harsh radiation and a lot of the other factors that are working against any living organism. So we feel pretty good about how clean we're able to keep Mars.
Thank you so much.
Sorry, Christine, may I ask a question to
Please.
Dr. Williford as well? I think many people have been asking me. I think, could you tell us a little bit about the helicopter? Do you know when Perseverance is going to park and for Ingenuity to do a little fly?
Yes, we're getting fairly close, I would say, to the helicopter phase of the mission. And the phase consists of about a week and a half of activities where we have to, first thing we have to do is drop the debris shield. So if you've been looking at these pictures recently of underneath the belly of the rover, there's a sort of dark little box-shaped thing that is the debris shield to protect the helicopter. We're going to drop that off very soon here in the next several days. Then we'll back away from that, take some pictures of it. Then we'll drive back to an area where we're going to deploy the helicopter that's pretty close to where we landed, about 12 meters. So, 12 yards ish, 15 yards to the American football players in the audience. And we'll drop the helicopter off, and we do that very carefully. So we do, sort of one step, we take pictures, send them back to Earth, make sure it all worked. We do another step and so forth over the course of about 10 days. And then we get the helicopter ready, and then we back away and we drive about 100 meters away, football field distance away, to a parking spot where we'll observe the rover, and it has 30 sols to run its technology demonstration mission, which is to really, they'll have mission success if they're able to do one flight. That will be a historic achievement in aviation and planetary exploration. But the plan is to try to do 5 flights and demonstrate flights of increasing complexity. And so that all should start unfolding fairly quickly here. We're getting quite close.
Really looking forward to the
Yeah, it should be exciting.
Yeah.
Well, we have a few more questions about Mars, but before we have those questions, I wanted to see if anyone has questions for our other panelists about the moon, about Ceres, about astrobiology, and because a couple of our panelists are focused on the moon and its geology and on its engineering, and one of ours focuses on Ceres. And I think I just froze. And I've launched a poll as well. So I'm going to give everyone 5 more seconds to answer the poll question.
I think we actually lost Christine. Y'all agree?
Yeah, seems likely.
Yeah, I think she froze.
Yeah. So I'm going to launch the rest of the PowerPoint that we had, and then, which she's probably gonna talk about this since we are concluding. So on the behalf of my manager, Christine Shupla, and myself and LPI, again, guys, thank you for joining us. We shall see you tomorrow, same bad time, same bad place. Thank you all panelists for your enthusiasm regarding what you experienced today. And we are so blessed to have you tonight. So Dr. Angles, get some rest. And we shall see you all on tomorrow. We have our final Paul That's lunch. So Christine, welcome back. So if you will, please share your thoughts about before you exit, and we will see you tomorrow.
Okay, thanks everybody.
Thanks everyone for joining.
Thank you so much to all of our panelists and speakers. We really appreciate it. Thank you so much. And thank you for all of you who joined us tonight.
Absolutely. Good night, everyone.
Thank you. Bye.
Good night. Bye.